Thank you. I'm very happy to give a talk about Subaru telescope update. This is sort of the suite of the Subaru instrument. As you can see, we have lots of instruments development activities, although we only have one single telescope. On the top, there's a SPAMCAM that is the first generation of the wide field camera, prime focus camera, followed by the next generation hyper prime cam. So prime cam is retired. Focus HGS, those are the standard Cassegrain multi-object spectra. Multi-object means only like a 20 multiplicity, so it's kind of old generation, but still active and very popular these days still. And HGS is more like high-def nasmith optical instrument, but those two classical instruments is still active. That's one of the features of the Subaru telescope. And also we have Keck AO, that is extreme AO. Main target is, of course, exoplanet hunting, which I mentioned a little bit later on. Okay, so this is just a reference where you can see the wavelengths and the spectral resolution coverage of all instruments. So I think one of the unique features of Subaru telescope among other 8 to 10 meter class telescope is, of course, the prime focus existence. Because it has a short focal length, we have a wide field coverage. So this is good at surveying faint objects over the wide area of the sky. But let me briefly look back the history of this prime focus. Initially, I think this is the beginning. The Ips, Angels, and Anderson worked out the wide field corrector, which is designed for the Keck telescope. Those are all glass material is all field seeker except those atmospheric dispersion correctors. And because of this limitation of the glass material, they have to split the wavelengths into two, red channel and blue channel, although the first lens was shared. However, the first lens is diameter reached up to 852. I think this is quite challenging at the late 80s or early 90s. But inspired by this pioneering work, one of the professor at NAOJ, National Astronomical Observatory of Japan, Nariai Sensei, worked out this reach up to this design, where he employs a very exotic low dispersion glass, FPL 51, built by, Ohara, the glass manufacturer in Japan. By introducing this exotic glass, the wide field coverage, 0.5 degree, over the wide range of the wavelengths from 0.4 to 1.0 was realized. However, the glass material is so exotic that it's very hard to build such a large diameter lens, 650 meter was necessary. Then the Canon joined us to develop the feasible corrector lens. The optical designer, engineer Takeshi-san, worked out this very innovative lateral shift ADC, atmospheric dispersion correctors. He succeeded in reducing the size of the corrector lens dramatically. And also the fast lens is a very practical BK7 equivalent lens, which is easier to manufacture. So this is the final design for the fast prime cam corrector. Then this is HSC corrector, also initially designed by the same Canon engineered. As you can see, I mean, the configuration is almost the same. We also introduced this lateral shift ADC here, and this is what we reached at the end. So the prime focus wide field camera enables this type of panoramic survey, panoramic surveys like this. This is a close-up view of the one of the survey field, the Cosmos field. So right now we have surveyed over the 100, no, 1,100 square degrees already. This is a close-up view of the one of the mass cluster galaxies at the redshift point. Well, 8, able 19, oh no, 1689. Compared with Hubble, of course, the Hubble image is of course sharper, but the depth uh, that we reach is almost similar to what we realized. In addition to the standard broadband images, broadband filters, we are now procuring the medium band filters. As you can see, we have a very special filter frames. Four quadrants has its own, different filters. So by rotating this, by rotating the instrument rotators, we can switch the filters. Uh, by doing so, we can reduce the number of the filter exchange time. Right now, it takes like a half an hour to exchange the one filter, so it's quite annoying. But rotating, you know, exchange mechanism reduce the exchange times quite dramatically. So we have basically the four sets of the filter. Each has its four filters. So in total, 16 filters will be prepared. And the reddish part is covered by the NSF grant. The PI is Stewart Observatory's professors H. Egami. So this is a US-Japan collaboration. And this will be available for the next semester, so you can write a proposal if you are interested in that through the Keck Subaru exchange time. So that is the story of the five prime focus, but we also have some interesting remarkable instrument, which is Extremeo. They call it Skexeo. And Skexeo is both a science instrument and a technology development platform. So routinely, they find out the exoplanet, as is shown on the lower left movies. And but we think regard this Skexeo as a test bed for the future missions like HWO. Because of the easy access to the Nasmith platform and very wide area, working field, it's quite nice to, use this Skexeo as a test bed. There are a lot of new technologies, like new concept coronagraphs tested routinely on this Skexeo test bench. A new instrument just showed up. That is a prime focus spectrograph. The prime focus spectrograph PFS is fairly developed through the very large international collaboration, including Caltech JPL and Princeton JHUs, and also the France Astronomy Institute in Marseille. This is a close-up view of the fiber positioner, which is developed by JPL. And you can see the reconfiguration of the fiber tips on this movie, which is very spectacular. So the reconfiguration and checking the position takes only like a few minutes. So it's very quick reconfiguration cycle. PFS is actually on Sky now, and they started the observation. The unique feature is, of course, the coverage all the way through the 1.2 micron. So J-band is covered by this spectrograph, and 2400 multiplicity is realized by this. So it's actually started the operation, open use operation last March, and so far we have four cycles of the observations. Well, we're actually in the middle of the fourth of open use round right now, and so it's nearly like more than 2 weeks or nearly 3 weeks nights are allocated for this because of the high demand of this new powerful instrument. We have another slide that shows you the new instrument being developed. That is a Ultimate Subaru project. Basically, it is a ground layer AO system realized by this adaptive secondary mirror, which is similar to what ESO has developed for the BLT. And we also employ the 4 laser guide star systems. So in the end, they will realize the 0.2 arcsecond spatial resolution in K-band over the field of view of 14 arc minutes times 14 arc minutes. So VLT has a similar instrument, but the field coverage is 7 arc minutes, and realized spatial resolution was 0.3 arcsecond. I think the difference between 0.2 and 0.3 comes from the superb image quality realized on the Mount K. So the schedule is that they are now both in the end of, the GLAO and wide field imagers are both in the end of final design phase, and final design will be completed by March 2026, followed by manufacturing, assembly, integration, test phase. So we hope that we see the commissioning start in the middle of 2029. So this will be the quite new powerful facility instruments. And I have one more slide, which is not the Subaru's facility instrument program, but I just want to let you know that we are working on the CMOS camera in collaboration with Homatsu, and that mosaic of 6 of the CMOS mosaiced into one, and that camera saw the first light this Monday, September 15th, right at the 2.3 meter Bock telescope at Stewart Observatory. So this CMOS can be read by 10 Hz, and this image is M standard 1. Of course, this is not I think the 20-second integration is necessary to realize this images, but each CMOS has a 2560 pixel times 10,000 pixels with a 7.5 microns. Hopefully, this will open up some new window to do high-speed astronomy. Thank you very much. This is the end of my slide.